I'm going to talk about sufficient condition for a polyhedron to be rigid and necessary conditions for the extendibility of a first order flex of a polyhedron to its flex. Okay, in this talk, I am going to focus on the main theme only. I mean, I will try to present the main ideas. But the other side of this intention is that I will not strive for the most general or rigorous formulations and will not emphasize the authorship of each result mentioned below. You can find all omitted technical details, historical information, and further references in the following articles of mine on which this talk is based. They were published in 2019 and 2020. Okay, so for me, a polyhedron is an oriented, connected, closed, two-dimensional polyhedral surface with non-degenerate triangular faces in Euclidean free space. Flexible polyhedron is a polyhedron whose spatial shape can be changed continuously by changing its dihedral angles only. I mean, a flexible polyhedron is such a polyhedron for which there is a continuous family of deformations which does not change the length of its edges, but changes at least one dihedral angle. Such deformations are called flexes. More carefully, I should say that this is a non-trivial flex of a polyhedron. Trivial flex do not change any dihedral angle at all, and non-trivial flex preserves the shapes of every face, but changes at least one dihedral angle. So the above mentioned continuous family of deformations that does not change the length of its edges, but changes at least one dihedral angle is a flex. And polyhedron is rigid if it admits no flex, non-trivial flex. Okay, so these are general and well-known definitions, I guess. Let me say that we know a lot about flexible polyhedron. I grouped these results in three. I organized this knowledge in three groups. The first group says that flexible polyhedra do exist. Moreover, they can be self-intersection free. And even in this case, they can have 9 vertices only, just one vertex more than a cube has. They can be of arbitrary genus. I mean, they can have as many handles as you want, and then can be even non-orientable. The second group of results is the following one. During the flex, flexible polyhedra necessarily keep unaltered the total mean curvature. It's a special quantity that is, in fact, is similar to the well-known total mean curvature of a smooth surface. The second very important quantity is the volume of the domain they bound. This volume remains constant during the flex. And also the Dehn invariants remain unaltered during any flex. In the third group, I want to properties that we know about flexible polyhedra is that the notion of flexible polyhedron can be introduced in every D space of constant curvature for every D greater or equal than 3. Moreover, in many such spaces, flexible polyhedra possess properties similar to A and B. Similar, but not always exactly the same properties. Sometimes we need some additions to these formulations. There are many open problems in the theory of flexible polyhedra and around this theory. The first open problem I would like to mention is that do there exist a flexible, closed, smooth surface? Yeah. So, I mean, it's a well-known problem of differential geometry, global differential geometry, that still remains open. The second problem is, given a polyhedron, is it flexible? So we are given a polyhedron, and we want to decide whether it is flexible or not. Yes, this is an open problem. The third problem is, describe all quantities that remain constant during the flex. At the previous slide, I have mentioned a few quantities that remain constant. But in this third problem, I want to know all quantities that remain constant during the flex. And the list of such quantities is still open. And the last question is, do there exist a self-intersection free flexible polyhedron with 8 vertices? I have mentioned that we know such example with 9 vertices, and we know that there is no such example with 7 vertices. But what about 8 vertices? This is again an open problem. My talk will contribute to the second question. Given a polyhedron, is it flexible? Of course, I will not solve this problem in all generality, but I will contribute to it. The starting point is Theorem I, which appeared nearly simultaneously in 2 papers, one written by Gaifullin and Ignashchenko in 2018, and the other paper is mine, published 1 year later, and I have mentioned it at the beginning of this presentation. The Theorem I reads as follows: let P be a closed-oriented polyhedron in Euclidean 3 space with non-degenerate triangular faces. So it's our main object. Let the set of edge lengths of P be Q linearly independent. Then P is rigid. Yes, I want to give some remarks to this theorem. Obviously, Theorem I is a sufficient condition for a polyhedron to be rigid. Yes. The second remark says that Theorem I is not a statement about generic rigidity. The main difference is that it requires the Q linear independence of edge lengths, not algebraic independence of the coordinates of vertices. This theorem is close to what is known as generic rigidity, but it's another statement. And the third remark is that, in fact, Theorem I is an immediate corollary of Theorem II, which is a tough nut to crack. Here is Theorem II. It was proven by Gaifullin and Ignashchenko in the paper that was already mentioned in the previous slide. Let P be a flexible, closed-oriented polyhedron in Euclidean free space with non-degenerate triangular faces. Then every Dehn invariant of P remains unaltered during any flex of this polyhedron. Let me remind you what is the Dehn invariant of a polyhedron. In fact, this object can be defined in several ways, and I prefer, and I recall you here, the most classical definition. So Dehn invariant is the sum calculated over all edges sigma of pi. No, of P. And we should sum the following numbers. Yeah, what is the first number? We should take any Q linear function defined on the real x with values in the real x again. And this Q linear function should be such that the value of this function at the point pi is equal to 0. If we suppose that this function f is continuous, then it is well known that this function must be identically equal to 0. But if we say nothing about continuity of this function, then it is known that there is a continuum of such functions. Yes, Q linear functions that are equal to 0 at pi. We in the definition of the Dehn invariant, we can take any of these functions. And we should take the value of this function at the real number that is equal to the length of the edge sigma. And then we should multiply this value by the internal dihedral angle at the edge sigma. In fact, we can take an external dihedral angle is the result will be the same due to this condition. So this quantity remains constant. This quantity, the Dehn invariant, remains constant during any flex for any function f of this type. On the next slide, I am going to formulate Theorem III. That is yet another corollary of Theorem I. The first corollary was...
Excuse me.
Theorem 1. Yes, yes.
I have a question. Should the
Yes.
function f be evaluated at the dihedral angle and then multiplied by the length, in fact?
Oh, yeah. Yes, right, you are. Yeah. Yeah, of course.
Okay,
of course. Thank you. Yeah. Yes. Yes, of course. Yes. Yes. L sigma should be multiplied by the value of f calculated for phi of sigma. Yes. Yes, sorry. Sorry. So let me continue. Yes. So Theorem III reads as follows. Let P be a flexible closed-oriented polyhedron in Euclidean 3 space with non-degenerate triangular faces. This is our main object. Let E be the set of the edges sigma of P. Let L be the set of the lengths L sigma of all ages sigma Yeah. So we have a finite number. L is a finite number of real, is a finite set of real numbers. And let a finite collection of real numbers, lambda 1, etc., lambda m, be a Q basis in the Q linear span of L, of this set of real numbers. What does it mean that it is Q basis? It means that we can write such a formula. L lambda is equal to the sum of some rational numbers multiplied by the elements of the base, of the basis. And alpha, sigma, j are rational coefficients in this expansion. So these are our conditions and notation. Then the conclusion of the theorem is that then for every flex of P and every j equal to 1, etc., m, the expression is constant during the flex. In this expression, alpha, sigma, j are exactly those rational numbers that appeared in the previous formula. And phi sigma stands for the internal dihedral angle of P at the H sigma. So it's very strange that some combinations of dihedral angles must be constant during the flex.
Victor.
Yeah.
There's a question in the chat.
Yeah, but I do not see chat at all.
Right, it says, can you define a Q linear function, please?
Q linear function. Yes, of course. You should take a usual definition of the linear function f of alpha x plus beta y is equal to alpha multiplied by f of x plus beta multiplied by f of y. And you should require that this equation holds for all alpha and beta rational numbers, not reals, but rational numbers. And x and y are real numbers. So yes, I hope it will be useful. So let me chat. Yes, now I see where chat is at least. Now let me try to. Thanks. Yeah, I'm I'm glad that it was helpful, useful. Okay, so let me say a few remarks to this theorem. Uh, 3. Each linear combination that is constant during the flex according to theorem 3 is equivalent to a similar linear combination with integer coefficients, not all of which are 0. In fact, we should just reduce fractions to a common denominator in this expression. The second remark is that for Bricard octahedra of all types, such linear combinations with integer coefficients are known explicitly for a long time. And the third remark is that Theorem 3 makes it possible to take a fresh look at the question of whether it is possible to extend a given first order flex of a polyhedron into its flex. So we are given a first order flex, and we are interested whether it is possible, whether this first order flex is generated by a flex. Let me recall the basic definitions. The first order flex of a polyhedron P with triangular faces and with vertices x1, etc., xv in Euclidean free space is a finite set of labeled vectors x prime 1, etc., x prime v, where each xi is in R3 and each x prime I is in R3 too, such that the following equations are satisfied for all I and j, such that the vertices xi and xj are incident to an edge of our polyhedron, to one and the same edge of our polyhedron. And dot here, dot stands for the dot product of two vectors, for the scalar product. These equations come from the formal derivative of the expression, yes, you can see it here, for the squares of the lengths of the edge incident to xi and xj, which are supposed to be constant. The edge lengths are supposed to be constant. Thus, when we differentiate this expression, we obtain this expression that is equal to 0. This is a standard motivation for the definition of the first order flex. And this is a, let me say, a standard equation for the first order flex. Intuitively, these vectors x prime 1, etc., x prime v can be regarded as formal velocities permitted by the age length constraints of the polyhedron P. In fact, similarly, the notion of an nth order flex can be introduced for all n greater or equal than 2. So we should just differentiate this equation n times. Okay. The standard idea to answer our question of whether it is possible to extend a given first order flex of a polyhedron into its flex is to split this question into the following sequence of sub-problems. A, B, C, I call this sub-problem. The first problem, A, reads as follows: given n that is greater or equal than 1 and an nth order flex of a polyhedron P, can we extend it to a higher, to the next order flex, to the flex of order n plus 1? Sometimes it's possible, sometimes it's not possible. Yeah, many people studied this problem. The second problem, B, says, suppose the answer to sub-problem A is positive for all n such that they are greater or equal than 1 and less or equal than some n star, for some large enough n star. Is it true that there is a continuous family of deformations of P which preserves its age lengths and which generates all nth order flexes? So are these higher order flexes generated by some flex? And the third problem reads, is it true that the continuous family of deformations of P obtained in sub-problem B is its flex? I mean that it is a non-trivial flex of P. Why it is non-trivial? Why at least one dihedral angle is changed? Yeah, so each of sub-problems A, B, and C is non-trivial and has not been fully resolved yet. Our approach based on Theorem I allows us to exclude all high-order flexes from consideration. So our approach is much simpler than traditional one. In order to present this approach, we need the following specific notation. This figure shows an age sigma. We start from an age. Then it shows the faces, two faces adjacent to sigma. This triangle and this triangle. These are two faces adjacent to this age. This figure shows also the vertices x sigma. This is x sigma, y sigma, 0 prime sigma, and 0, 2 prime sigma. These are vertices of these two faces. And it shows also the normal outward normals, n prime sigma and n2 prime sigma to the faces, to these faces. In fact, this theorem, this notation is highly overdetermined. I mean, first of all, I should take the vertex, the H sigma, but I can say that this vertex is X sigma, not Y sigma, and this is Y sigma, not X sigma. This is my choice. And I should take, if I take, say, this H, it means that this vertex will receive the notation, will be denoted by Z prime sigma or Z2 prime sigma, not X sigma. So one and the same vertex will have different notations for different ages sigma. So in this sense, this notation is overdetermined. And nevertheless, it is useful because it make it possible for me to formulate the following theorem, available in my paper mentioned at the beginning of my talk. So suppose the conditions and notation of theorem 3 are fulfilled. It means that we have a polyhedron, two-dimensional polyhedral surface in the three-dimensional Euclidean space with non-degenerate triangular faces. Suppose also that this collection of vectors, this is a collection of vectors, is a first order flex of P, and moreover, we suppose that this first order flex can be extended to a flex of P. What is this notation? We have the vector A sigma of the first order flex corresponds to this vertex X sigma. The vector B sigma corresponds to this vector Y sigma, this vertex of the polyhedron, and so on. So these are conditions of our theorem, and the conclusion is that then for every j from 1 to n, this equality holds true where the vectors g sigma, g prime sigma, g2 prime sigma are defined by the following long but explicit formulas via position vectors of the vertices of the polyhedron. So first of all, let me, so this theorem says that if the first order flex of a polyhedron can be extended to a flex, then the vectors of this first order flex must satisfy some additional equation that is new, that was not declared in the definition of the first order flex. Now let me try to explain the structure of this equation first of all. So these vectors g sigma, g prime sigma, and g2 prime sigma are defined in terms of 2 more or 6 more vectors, R sigma, S sigma. In the cases when cosine of phi sigma is 0, we should always take R sigma, exact, some particular vector. If sine of the dihedral angle is equal to 0, then we should use another expression. But if neither sine nor cosine of the dihedral angle is equal to 0, we can choose any of these vectors R and S as G sigma, and so on for prime and 2 prime. And what are these vectors? R sigma. They are given by some long but explicit formulas in terms of position vectors of the vertices of the polyhedron. I do not believe that it is possible for you to understand something in these formulas. Just notice that they are explicit. And for vectors S sigma, we have another set of explicit formulas. So let me return to this theorem 4 and say it again, that it's very strange, but we have some special, some new, specific, unusual, I will say, unexpected, additional equation for first order flex, for the first order flex of a polyhedron. And these coefficients are prescribed. They are rational numbers or even integer numbers. And they are prescribed to us by the age lengths of the polyhedron. And these vectors G sigma, G prime sigma, G2 prime sigma, they are also given to us as soon as the polyhedron is given. So this is a linear equation for the first order flex. I will refer it as a red equation in the future. So let me say a few remarks. In my paper, published in 2020, an example of a polyhedron is given for which the system of red equations is not a consequence of the system of equations in the definition of the first order flex. This is what I mean when I say that red equations are new. Hence, for some polyhedron, it can occur that some of the red equations are violated for some of their first order flexes. So according to the definition, the first order flex exists and we can calculate it somehow and we can verify that this is a first order flex, but it does not satisfy the red equation. In this case, we can answer in negative to our question of whether it is possible to extend the given first order flex of a polyhedron into its flex. The answer is negative. No, it is not possible. In fact, I am not aware about any previously published results similar to Theorem 4, neither for polyhedron nor for bar and joint frameworks. Such.
Victor, there's a question in the chat, if you can look. It says, where does the basis come in?
Why? Yeah. Where does the basis come in the coefficient alpha depend on the basis? Yes, of course. Yes, it depends on the basis. Yes. And let me go back.
So my question is whether the result is independent of that basis. So your formula holds independently of what basis you
Yes,
use.
yes, it is independent. Yes, I can choose any basis number, any basis, any. And then this formula holds true. And then the same coefficients should be used and can be used in theorem 4. And the basis is arbitrary. Yes. So let me return again. Let me return here. So from my point of view, theorem 4 is, in fact, it's new, both for polyhedra and for bar joint frameworks. Okay, let me recall the logical relationship of the above presented results. So the basis of all these results is theorem 2 that reads that the Dehn invariants remain unaltered during the flux. This theorem 2 implies theorem 3 that reads that some expression is constant during the flux with rational or even integer coefficients. And this theorem implies theorem 4 that reads that for every j from 1 to n, some red equations holds true with the same coefficients that appear in theorem 3. Okay. So this was so the origin of all these results is theorem 2 and of theorem 2 and the statement that Dehn invariants remain constant. Now I want to note that the Dehn invariants are not the only source of equations similar to the red ones. I mean here necessary equations for a given first order flux of a polyhedron to be extendable to a flux. There are some other equations of this sort and they are different from red equations. Another source of such equations is the rigidity matrix. More precisely, every 3v minus 6 times 3v minus 6 minor of the rigidity matrix, where v is the number of vertices of P, can be considered as a source for such equation. Let me explain it in short. Such a minor is a homogeneous polynomial in the coordinates of the vertices of P that is identically equal to 0 during the flux. Because in every moment of the flux, we have a first order non-rigid polyhedron. Thus, its rigidity matrix has corank 6, more than 6, sufficiently large corank. Differentiating this minor with respect to the parameter of the flux at the starting point of the flux and replacing the derivatives of the variables with the corresponding vectors of the first order flex of P, we obtain some mu equations similar to the red ones. Necessary conditions for a given first order flex of a polyhedron to be extendable to a flex that arise from the rigidity matrix are too complicated and too long to be written out here explicitly. Just note that for some polyhedron, some of the equations arising from the rigidity matrix are violated for some of the first order flexes of the polyhedron. So I mean these mu equations are not consequences of the equations from the definition of the first order flex. I can explain you this fact by simple pictures. This figure shows a tetrahedron T, one of whose face is additionally triangulated. This is an additional vertex, and this face is split into 3 triangles. But they are located in the same plane where the initial triangle was located. For such a polyhedron, at least one of the equations described on the previous slide is not a consequence of the standard system of equations for the first order flex. In fact, red arrow is perpendicular to the additionally triangulated face of T. It represents a first order flex. The vertices of all other The velocities of all other vertices are equal to 0. This is a standard and obvious fact. This is the first order flex. Okay. Green arrow lies in the additionally triangulated face of T. It represents an infinitesimal deformation, not a first order flex, but infinitesimal deformation along the set of all first order non-rigid polyhedra. The velocities of all other vertices are equal to 0. So now it seems to me obvious that if you move in such along the set of all first order non-rigid polyhedra, it means that if you deform your polyhedron in such a way that it remains to be first order non-rigid, then you should move along green arrow. You should move this vertex within, you should move this vertex within the plane of this additionally triangulated face. And if you want to have a first order flex, you should move this vertex in the direction perpendicular to this plane. But it is not possible to have both such motions simultaneously. So it means that red equations are violated for such a deformation. Okay. So hence, for some polyhedra, some of the equations arising from the rigidity matrix are independent of the equations from the definition of the first order flex. So red equations and the equations that I didn't write down explicitly, that equations that were originated that arise from the rigidity matrix, they are independent of the standard equations of the first order flux. In conclusion, I would like to note once again that many problems related to the topic of the talk are still awaiting their solution. For example, do these new equations imply that the volume bounded by a flexible polyhedron is stationary? We know that volume of the flexible polyhedron is constant during the flex, but this result was obtained by, let me say, algebraic methods. It was not obtained, we do not know any solution of any proof of this theorem that uses first or second or higher order flexes. The reason is another for the preservation of the volume. But maybe these new equations will make it possible to prove that already the first order flex that for the first order flexes, the volume is stationary.